Okay, I've got a really cool integral to show you guys today, and this one I've got a little help on. So let's look at our main goal. Our goal is to calculate the integral from 0 to 1 of 1 over 2x, but that's inside the floor function, minus 1/2 of the floor of 1 over x. And so notice it looks like these should be the same, and thus they should cancel out to be 0, except this one has the half inside the floor function and this one has the half outside the floor function. So this is really measuring what do we lose by putting the half inside the floor function instead of outside the floor function. Okay. Great. So along this path, we're actually going to have two tools which will make our solution go a little bit cleaner. The first one is this pretty simple integral to calculate. So if k is a natural number, we've got the integral from k to k plus 1 of the floor of u over u squared du, and we'll see that that's 1 over k plus 1. And then next we have this nice result about harmonic numbers, namely that if we take the limit as n goes to infinity of the mnth harmonic number, so we'll denote that by hmn, minus hn, the nth harmonic number, we get the natural log of m. Okay, great. Where as a reminder, the nth harmonic number is defined as the partial sum of the harmonic series. In other words, it's the sum k equals 1 to n of 1 over k. Okay, so I'm going to throw this to black pen, red pen. He's going to do the first tool for us. So let's see that.
For tool number 1, notice that here we have the floor of u, and we're integrating this over the interval k to k plus 1, where k is just a natural number. So on this interval, the floor of u is just equal to k. Therefore, we can just write this as the integral going from k to k plus 1, and then we have k over u squared du. And then, of course, to integrate 1 over u squared, that will give us negative 1 over u. And I just have to multiply by that k, right? So, integrating that, we get negative k over u. And then, of course, we will have to plug in the k plus 1 first. We get negative k over k plus 1. And then we will have to subtract. Plugging k here, we have negative k over k. Alright, now this part is actually just plus 1, and this is negative k over that, so I will have to get a common denominator, which is k plus 1, k plus 1. K plus 1 on the top, combining with negative k, we just get a 1, and then over the bottom is actually just k plus 1. And there we have it. For the tool number 1, we actually just end up with 1 over k plus 1.
Okay, so now we've seen the first tool, how that is proven, and now we're going to move on to the second tool, which has a really interesting solution. So let's go ahead and look at this. So we have the limit as n goes to infinity of, so the mnth harmonic number minus the nth harmonic number. So I'll go ahead and rewrite those as sums. So that's going to be the sum k equals 1 to mn of 1 over k minus the sum k equals 1 to n of 1 over k. But now notice that all of these terms in this second sum are contained in this first sum. So what that means is that we can write this as a single sum if we start, instead of at k equals 1, we'll start at k equals n plus 1. So notice we can remove all of these terms from this sum if we start at n plus 1. So let's just go ahead and rewrite that. So we've got the limit as n goes to infinity of the sum k equals n plus 1 up to m times n of 1 over k. Now the next thing that we want to do is reindex. And we're going to reindex in the following way. So our old k is going to become n plus k. Okay, so now let's see what happens with our bounds of summation. So our old lower bound was k equals n plus 1, which we have right here. Now that's going to go to k equals 1 if we're replacing k with n plus k. And then furthermore, our old upper bound was k equals mn. But if we replace k with n plus k, well, let's just go ahead and calculate that on the side. We have n plus k equals mn, so that's going to make k equal to mn minus n. In other words, it is n times m minus 1. So that makes our new upper bound n times m minus 1. So that's going to allow us to rewrite this sum in the following way. We have the limit as n goes to infinity of the sum k equals 1, that's our new lower bound, up to n times m minus 1. And now that k is going to become n plus k. Now what I want to do is notice that n is a constant with respect to the summation, so I can go ahead and factor that thing out, and that's going to leave us with the limit as n goes to infinity of 1 over n, and now we have the sum k equals 1 to n times m minus 1 of 1 over 1 plus k over n. Okay, so let's just check to make sure that makes sense. So if we move this 1 over n inside the sum, the n is going to multiply on this denominator, and we will get n plus k back. Okay, now I want to rename these things, and I want to rename them in a way that we will actually visualize this infinite sum as a limit of a Riemann sum of a particular integral. And I'm going to do that in the following way. I'll go ahead and let delta x equal 1 over n. And then I'll let x sub k equal 1 plus k over n, which notice that is 1 plus k times delta x. Great. But notice that's going to go ahead and make x0 equal to 1. And that's going to make the upper bound of this sum, x sub n times m minus 1, equal to, well, if you plug n times m minus 1 into this, notice you're going to get 1 plus n times m minus 1 over n, but that's just m. So, just to reiterate what we're doing is we're noticing that this is a limit of a Riemann sum of some integral. And which integral it is will be clear once we write the next line. So notice now we can write this thing as the limit as n goes to infinity. Instead of 1 over n, we're going to go ahead and write that as delta x. And now we have the sum k equals 1 to n times m minus 1, 1 over xk. But this looks exactly like the Riemann sum for the integral from 1 to m of 1 over x dx. So notice the delta x term becomes our dx, and then our 1 over x to the k becomes, x sub k becomes 1 over x. But this integral is pretty easy to do. We can just take the antiderivative. We get the natural log of x evaluated at 1 and m. Notice that gives us the natural log of m after evaluating, because the natural log of 1 is 0. But that's exactly the result that we wanted. And so that finishes proving this second tool. And now we're ready to go ahead and look at our goal integral. So the first thing I'm going to do is notice that this is an improper integral. The integrand has a discontinuity at 0, so I need to set this up as some sort of limit where the lower bound is approaching 0 from above. And I'm going to do that in the following way. I'll make this the limit as n goes to infinity of the integral from 1 over 2n up to 1. Now this is like a slightly non-standard way to do it, but all we need is for this thing to be approaching 0 from above, and this does it. So 1 over 2n clearly approaches 0 from above as n goes to infinity. Okay, and now we'll have, this is the floor of 1 over 2x minus 1/2 the floor of 1 over x dx. But now, inside the limit, these are no longer improper integrals, so that means we can break this up into two parts. And so I'm going to write this as the limit as n goes to infinity, and then we'll have our two parts, the integral from 1 over 2n up to 1 of the floor of 1 over 2x dx, minus 1/2 the integral from 1 over 2n up to 1 of the floor of 1 over x dx. And now we're going to have a little more help to calculate this first integral. So let's go ahead and see what that becomes.
Okay, to integrate the floor of 1 over 2x from 1 over 2n to 1, first we will take a u sub. So I'll write it down right here. Let u be the inside, which is 1 over 2x. And then of course do the usual business. Let me actually multiply both sides by x and divide both sides by u. So we get x is equal to 1 over 2u. It's easier to take the derivative this way. And then we get the dx right away. and that's going to be the derivative of that, which is negative 1 over 2u squared du. Then we can take this integral to the u world, but don't forget that here we have x is from 1 over 2n up to 1. So be sure to take the numbers to the u worlds as well. So we get here, when x is 1 over 2n, we put it right here, and you see this 2 and then the 1/2 will cancel. So that will give us 1 over n, which is just an n by itself. Then we put 1 right here, so of course that will be 1/2. And then here we will have the floor of u, and then the dx is precisely that, so we multiply by negative 1 over 2u squared du like this. Now, we have this negative, which is actually pretty good because that will help us to switch the order of integration, and we will see that this right here becomes the integral going from 1/2 to n. And this negative right here is no more because we used it already. Alright, we do have the 1/2, let me just put that all the way in the front. And then we have the floor of u over u squared, like so, in the u world. And that's pretty good. Now, here is a small thing that we can fix before we proceed. Notice we do have floor of u over u squared, and this integral is starting at 1/2 up to n. Have a look though. When we have 1/2 inside of the floor function, what do we get? We actually end up with 0, right? So in fact, the interval from 1/2 to 1, that will give you 0 area. So it doesn't matter. So I can actually integrate this, right? Let me just write down 1/2. We can actually start at 1 instead. Because again, from 1/2 to 1, this right here will be 0. 0 over that will be 0. It has no area. So we can just change that to 1. And then we still go up to n. And then we still have the rest. Floor of u over u squared du. Okay, what can we do next? We still have to face the fact that we are integrating something with floor, right? And to do so, we have to break this into pieces. And this is how we can do it. Still write down the 1/2, good. And every piece, we just go ahead and integrate them individually and then add them up. So we have to use a summation. So let me just open a summation here. I will use k as the index, and k will be starting at 1. Go up to n minus 1, right? And let me just double check Professor Penn's notes. Yes, it's correct. Yeah, I got it right. All right, so that's what we have. And then, of course, the rest is just the following. I will do this in blue because why not? Here, we will have the integral starting at k, right? Because, you know, k goes from 1 to n minus 1. And here, it's a time that we will actually have k plus 1. And then the rest is the floor of u over u squared du. And does this look familiar? Yes, because we did that already. So with that being said, here is the deal. Here we have 1/2 all the way in the front, and then we still have the summation going from 1 to n minus 1. And all in all, this will give us 1 over k plus 1. So of course, I just have to write that down. That's all. Then, if you would like, you can fix this a little bit before you proceed. You can subtract 1 here, and just have to add 1, add 1. So, you can look at this as 1/2 times the sum going from k is 2 to n, because I'm adding 1, and then I will just have to minus 1. Does this look familiar? It looks almost like 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus da 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 up to 1 over n, right? Namely the harmonic number. But the problem is that here we have k starting at 2. Well, it's okay. Let me just add the first term and then subtract the first term. So all we have to do is the following. We'll just write this as 1/2 times this. It's the same as saying the nth harmonic number, and then we just have to minus 1 like this. Because this is 1 over 1 plus 1 over 2 plus 1 over 3 plus da 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 up to 1 over n. When you minus the first term, which is 1 over 1, you do end up with that. And with that, we are so done. That's it. Yeah. And thank you, Professor Penn, for having me on your channel. I look forward to have more collab with you.
Okay, good. So we got that first integral. That's equal to 1/2 of hn minus 1, where hn is that nth harmonic number that we've been working with. So now let's go ahead and calculate this second integral, and we'll do that on the side. So let's see, we have the integral from 1 over 2n up to 1 of the floor of 1 over x dx. And we'll use the same kind of strategy that was used in this first integral. That is, we'll use u substitution and the like. So let's go ahead and set u equal to 1 over x. So notice that's going to make x equal to 1 over u, and similarly that's going to let dx be equal to negative 1 over u squared du. Okay, good. And then also notice when x equals 1, that's going to make u equal to 1. And then when x equals 1 over 2n, that's going to make u equal to 2n. Okay, great. So that's going to turn this into the integral from 2n up to 1 of negative the floor of u over u squared du. Okay, so let's see where all those parts came from. So notice this dx component became this minus u squared du, and then our floor of 1 over x became our floor of u. Okay, great. Now the next thing that I want to do is take this minus sign, just go ahead and get rid of that by changing the order of integration. So we'll change the order of integration from 1 up to 2n. And then, since this is a floor function, it's really obvious to break this up into a sum over the intervals 1 to 2, 2 to 3, and so on and so forth. And so we'll do that. So this is going to be the sum, k equals 1 up to 2n minus 1, of the integral from k up to k plus 1 of the floor of u over u squared du. Okay, fantastic. But notice, by this first tool, we can replace this integral with just 1 over k plus 1. So here we have the sum from k equal 1 to 2n minus 1 of 1 over k plus 1. But the next thing that we can do is re-index this thing. So notice we can re-index this by sending k to k plus 1. That's going to change this to a k, make this thing start at 2, and then it's going to end at 2n. But notice that's exactly the 2nth harmonic number, but we're missing the very first term, so we can write this as the 2nth harmonic number minus 1, because again, we're missing one term. Okay, so let's go ahead and put that value in here for this second integral. Okay, and now we can go ahead and simplify this stuff that's inside of these big parentheses and then take the limit using our second tool. So I'm going to go ahead and bring a half out of the whole limit, because notice that's a common factor. And then we're going to be left with hn minus h sub 2n. In other words, the nth harmonic number minus the 2nth harmonic number. Now the next thing I want to do is take a minus sign out of that as well, in order to make it look exactly like our tool, although we can infer what's going on without doing that. So that's going to give me minus a half, and then we have the 2nth harmonic number minus the nth harmonic number. But we calculated that limit in general just before and found out that that was the natural log of 2 in this case. So we have, this is minus 1/2, the natural log of 2, but we might as well take that minus half that's outside of the natural log, bring it inside, in order to write this as 1/2 times the natural log of 1/2. Okay, so now let's look at our very beginning, right here, and our very end, and there's some nice structure to it. Here we're multiplying the half on the inside of the floor, here we're multiplying the half on the outside of the floor, and what we ended up with was 1/2 times the natural log of a half. Okay, I'm going to go ahead and clean up the board, and then I'm going to state a fact of what's going on in general here. Okay, so now that we've looked at our result, in other words, the integral from 0 to 1 of the floor of 1 over 2x minus half the floor of 1 over x is equal to 1/2 the natural log of 1/2, there's actually a more general result that is due to Riemann, and that is for alpha in the interval 0 to 1, we have the integral from 0 to 1 of alpha over x, but that's inside of a floor, minus alpha times the floor of 1 over x is actually equal to alpha natural log of alpha. So notice we did a very special case of this where alpha was equal to a half. Now, kind of question that we could go to from this is what happens if alpha is in the interval 1 to infinity? And so a special case of that, which looks a lot like what we just did, is what if we do the integral from 0 to 1 of 2 over x inside of the floor function minus 2 times the floor of 1 over x. What would we get in that special case, and then what would we get in the general case? So I think this is not super hard to work out, especially using the tools from this video. So post in the comments if you find the solution. Also, I'd like to give a big thanks and shout out to Black Pen Red Pen for being on my channel, and hopefully we'll do some more stuff in the future. Okay, we're done.